Hi, welcome back to the mechanical channel. We're going to do a dynamics problem here, specifically a question. It's the energy method, chapter 14. It's question 1463. And it's fairly simple, but the thing with the energy method is, you can talk yourself into including things that shouldn't be included. So um, let's have a look at it here. I'm not going to show the question. The question's this is it in its entirety. It's a flywheel, or it's otherwise a large wheel. Okay, stationary, mounted on a stationary axle. So like that axle, and you know, book speak for stationary. So it's not rolling, just spinning. If you understand the difference, not the wheel's not translating. Anyways, and it's got a cord hanging off there, and it's got a weight here, weight B. This is wheel A. And weight B is 96.6 pounds, which is a nice gift because, the mass will be easy. Okay? And weight A, the wheel weighs 200 pounds. Let's put that here. Okay. And the K of the wheel, here's some known values. K, the radius of gyration, okay, is 2 feet, which is related to the mass moment of inertia. It's just a child of it. That's saves us having to compute it. We don't know the dimensions anyways, the thickness of the wheel, so we have to know that. The systems at rest, and here's the dynamics part. The systems at rest with B, the block here, and then it drops 8 feet. Okay, so it drops 8 feet. So this moves down 8 feet like that. Okay. V naught equals 0 at rest. That's all, I guess. Weight of A and weight of B are given there. RTF. Okay. Angular velocity of A, omega A, after B has dropped 8 feet. 8 feet. Okay. All right. So obviously potential energy is happening here. Let's just make a little list here. Okay. Initial energy. So it's an energy balance. You got energy to begin with, and then it can't be destroyed or created. So you got the same amount of energy at the end. But the initial energy is potential energy of the block. Okay, initial energy, potential energy of block B. Okay. Final energy, if I can spell, final energy is kinetic energy of both block B and wheel A. Now, here's the thing where you might want to add something in. Is there any work being done? Is there any third form of energy? And it's pretty obvious, I think, that you start off with potential energy, and if you call this the datum, right, you end up with no potential energy. You've converted it all to kinetic. But in the process, is work being done? Okay? The answer is no. I know there's a torque times theta thing. Okay, I know there's an energy value. There's a spring energy and friction energy, and then there's energy of a input energy due to torque. This has no device connected to it. It has this weight connected to it. It's a bit confusing, I got to admit, but there. So here's the realization, still under the known column. There is no external device driving wheel A. There's no electric motor driving it. There's no chain drive, belt drive, nothing. Okay. Only PE of block B is driving it. is causing rotation. There's also no friction. We're neglecting friction. Also, frictional effects are neglected. They won't always be neglected. If you knew of a bearing friction here, you would include the bearing torque times the angular displacement theta. But there's no mention of it. We're going to neglect it. If they're a nice set of bearings, it's negligible anyways, like ball bearings. Okay. But again, you might be inclined in your energy balance to say, oh, the initial energy is potential, and the final energy is kinetic of the block and kinetic of the wheel, plus torque times theta, torque being force times distance. Torque times theta, the torque, it is true that there is a torque here. And it arises due to the weight of block B acting on this radius, which I forgot to put in here. The radius is 3 feet, eh? R 3 feet. It is true that there's a torque acting there, but that is the torque is the manifestation of the potential energy of B. It's gravity. Gravity is causing the torque. Well, we're already accounting for gravity in PE. If we also then had a torque on there, we would be double accounting for gravity. You can't do that. That perhaps is the crux of this question. The difficulty of the question. So U initial energy equals U final. Okay. All right. Well, let's move that up a little bit. Initial energy, PE of block B. Final energy, kinetic energy of B plus kinetic energy of A. So it gets split into two, okay? Where potential energy of B is obviously mgh, right? Well, we don't have to say mgh because we have the weight already. So the potential energy of B is weight of B times, let's just call it ZB. Okay. And kinetic energy of B is, of course, 1/2 mv squared, 1/2 mb vb squared. Okay. And kinetic energy of A, the wheel, is our friend 1/2 I omega squared. That's IA. Okay. So there's our three energies. But we've got too many unknowns, right? The question says, well, what's the velocity of A? What's omega A? That's what we're after, omega A. But VB is unknown as well. Well, you have to relate the two. Two unknowns. So there's two unknowns, okay? Velocity of B and omega A. Two unknowns. VB and omega A. Therefore, we need another equation, and you know which one that's going to be, I hope. Here's the other equation, okay? Here's the other equation. Okay, it's velocity of B, the tangential velocity of B is the radius of A omega A. Now we want omega A, so let's solve VB in terms of omega A. There it is. That'll allow me to substitute that in. I can substitute that into the kinetic energy of the block here. Okay. So we have this now. This is the final setup for the energy balance. Okay. We have the potential energy of B. That's the weight of B times ZB, the distance through which it falls. And all that energy manifests, it turns into 1/2 mass of B, VB squared, plus 1/2 mass moment of inertia of A, omega A squared. Okay. And then here's the sub. This, right? This goes there. Okay. Weight of B. I'm not going to put numbers in yet because maybe some stuff will cancel out. 1/2 mb. Now don't forget, it's RA omega A squared. You got to square the whole thing like that. That's a gigantic A subscript. Okay. plus 1 half omega, or sorry, IA, sorry, not squared. Whew, terrible. Omega squared. Okay. Nothing cancels. There's no free lunch here. Okay, that's omega A. But let's I guess there's one other equation, and that's the I alpha, or I, the moment of inertia of the wheel. But let's just in real time. That's a nothing thing. It's k squared, right? K squared times mass, right? So it's a nothing thing. Okay. Here it is. I'm going to put the numbers in now. Weight of B, 96.6 pounds. It falls through 8 feet. ZB 8 feet. Now don't put a negative there. There's no, with energy, no such thing as a negative energy. So the use of negatives, I know it's falling down. I know I drew it and it's falling down like that. That in the energy method, you don't take into account this falling through a negative value. It doesn't make any sense. You can't have a negative energy. So you just use, this is the potential energy to begin with, and there are no negatives there. 1 half mass of B, well, that's 96.6 over 32.2, which is 3 slugs. Okay, 3 slugs. Here it is, your 96.6 over 32.2 slugs. RA, well, that's 3 feet, squared, omega A squared. I just broke that out. R omega squared. So 3 feet squared, omega A squared. Plus, okay, 1 half IA. Well, that's k squared mass. Okay, k squared mass. K is 2 feet squared. Mass is 200 over 32.2 slug. And then I ran out of space here. And then, so that's one half. This is I right here. That is I equals k squared times mass. All right, that's the definition of, well, that's how radius of gyration is related to mass moment of inertia. Okay, so that's it there. Okay, 2 feet. Look at that. I screwed that up. 2 feet squared. The square goes on the outside there. 2 feet all squared. Okay. Mass 200 about 32.2 omega A squared. Oh, look at that. I ran out of space. Okay, it's way over there. Okay. So I've got 2 terms of omega A squared. Let's blend some numbers together. Okay. I'm going to do one more line here. So I got 96.6 times 8. So I got 772.8 foot-pounds of energy. That's the motive source here. Okay, that's the potential energy, right? And that equals, let's do this one, 1 half times 3 slugs times 3 squared, which is 9. Okay, so it's 13.5 omega A squared. 13.5 omega A squared. That's what that turns out to be. And then the rotational energy term, the rotational kinetic energy, 1 half, okay, 0.5 times 2 squared, k squared, that's 4, times 200 divided by 32.2. Okay, so it's 12.42 omega A squared. It's about evenly split, hey? It's about evenly split. In other words, this amount of energy, a little bit more than half goes into the block, and a little bit less than half goes into the wheel. So I'll process this further. Omega A equals, okay, all right, 772.8 divided by, obviously, the sum of those two, 12.42 plus 13.5, 25.92. And of course, square root because it's omega A squared. Omega A equals, okay, invert that, times 772.5, so 0.8, square root, 5.46 rads per second. That's the answer, okay? Fundamentally, a pretty straightforward question. Once you get past this idea that there is no actual external torque acting on it, the torque acting on the wheel is essentially the same phenomena as the potential energy. So don't double account for it. Okay. All right. Good luck to your efforts in the course.